Hi there everybody, welcome to another MCAT ACE lecture, and this one today is going to be on electrochemistry. So let's get started with a brief outline in terms of what we're going to intend to cover in this lesson, and then we'll get moving. So the first thing that we want to cover is just going to be a basic overview of electric cells and how they work using some redox chemistry. So here we will use some diagrams that are going to help illustrate, and it will include basic concepts like electrodes, so the cathodes, the anodes, and electrolyte solutions, as well as salt bridges. So we'll look at some diagrams that set all of that up. And then after that, we're going to take a look at half reactions and reduction potential, so the energy associated with the cells. We're going to look at the chemistry going on, that's the half reactions, and that's what drives the battery or the cell to work in the way that it does, to either require a current or provide a current. Those are the two different types of cells. So we'll briefly discuss concentration cells and what those are. It's where the electrodes are going to be identical to one another, but they can still generate a current because the concentrations of electrolyte are different. And then we will move on to some of the math that involves things like free energy, cell potential, and the Nernst equation, which can relate cell potential to free energy and equilibrium. So if you remember Q or K, we're going to tie that back in there with the state of the redox reaction. And then finally we'll wrap up by looking at some common types of batteries, and we do have a couple of sample questions that we'll take a look at. So let's go ahead and get started with this. So there are several important parts to a battery cell, which include the anode, the cathode, which are a way to electrically connect the two that are typically done through a salt bridge connection. And this is with electrolyte carriers. So the anode is associated with a negative charge, and it's the location where oxidation is going to occur for the redox process. So that means it'll be used to generate the electrons, as the metal at the electrode is going to lose electrons there. So maybe you remember your little mnemonic like Leo, Gur, or oil rig. Loss of electrons is oxidation, gain of electrons is reduction. So on the flip side, you'll have the cathode. That's going to be the positive end. That'll receive the incoming electrons in order to reduce the material and deposit it onto the electrode, whatever metal we're working with at that electrode. And the two electrodes will commonly be in electrolyte solution of the corresponding metal for that electrode. So that's how at the anode the metal is going to give off those ions as the electrons are lost, and then in the cathode solution the ions that are in that solution will receive the electrons and they will deposit as metal onto that. So for instance, a metal copper electrode might be in a copper 2+ electrolyte solution, and that will allow copper ions to either be removed into electrolyte form from the metal during oxidation, or to be deposited from the electrolyte form onto the metal electrode during reduction. Since the electrodes are kept in separate containers and their respective solutions, a salt bridge is used to help supply the needed electrolytes, because you may be depleting your electrolytes as you're going along and you're depositing. So you need to make sure that you have some sort of a salt bridge connection that allows the electrolytes to be replenished and connect those two to one another. And that'll help supply the needed electrolytes as the concentration shifts around during the redox process. So let's take a look at the basic visual setup for a cell that we're talking about. All right, so this here is the basic setup where you're going to have two electrodes that are found in their respective electrolyte solutions with a common salt bridge that connect the two. So these type of cell setups are common in general chemistry labs and a lot of course images that you'll see. This image would represent what's called a galvanic cell. And then sometimes those are also known as voltaic cells. I'll be calling them galvanic cells as we move along here. And you can see there's a voltmeter at the top of this. And the voltmeter at the top suggests that an energy current will be produced in this redox setup. And that would also imply that the reaction is going to occur spontaneously. So now we start getting into a little bit of the discussion with free energy and cell potential. And if this redox is favorable, it'll occur spontaneously and the electrons will be passed through this voltmeter, and we will generate some sort of a current. So galvanic cells are going to generate currents, and you would see them with that voltmeter. So let's look at this with a little bit more detail. All right, so here is the same diagram with some additional information regarding the electron flow. And notice that the electrons are sourced at the anode, if you follow the arrows, and they flow to the cathode. Okay, so the salt bridge is responsible for connecting the solutions and replenishing the needed electrolytes that are going to be required during this redox process. So you can see the I- and the manganese plus in the respective electrolyte solutions. It's going to be important that we continuously supply as that's being consumed. All right, so electrolytic cells are going to be kind of similar, but there is a difference here. So electrolytic cells differ from galvanic cells in that the redox reactions that are being driven here are not going to be spontaneous. So another way of saying this is that they have a positive free energy. So if you remember Gibbs free energy, the positive is going to be non-spontaneous, the negative is a spontaneous reaction. And relating it to the cell potential, if we have a positive free energy, then you have to have a negative cell potential. So this is going to mean that they are consuming some sort of current to drive the redox rather than producing it. So back where that voltmeter was, on this example right here, you would have some sort of a battery or something that could generate a current in place of that. Okay, and as we were saying, this means the electrolytic cell is going to require an external current supply in order to successfully transfer those electrons from the anode and the cathode. And that is because we are dealing with a non-spontaneous reaction at this point. So I want to bring up the idea of a concentration cell here. A concentration cell is a special type of battery cell in which the anode and the cathode are made of the same material, the same metal, but they exist in electrolyte solutions of differing concentrations. Okay, so in a case like this, the imbalance of electrolytes between solutions will drive the electron transfer, and that is what is going to generate the current as the two solutions look to balance one another's out in their concentration value. So this is really trying to establish an equilibrium between the two electrolyte solutions as they are passing these ions back and forth. So we're going to take a look at a half reaction here and start discussing that. So the chemistry that occurs at each electrode can be expressed as either an oxidation reaction or a reduction reaction. And these individual reactions are known as half reactions, and they can be combined to show the overall net redox reaction. So let's look at a common example for a lead-acid battery. So what we have here, we can see the half reactions for a lead-acid battery setup. The anode is using solid lead metal, which is oxidized to lead 2+ in the form of lead sulfate. And the cathode half of this reaction is going to show that lead dioxide is going to lead to lead 4+, which is reduced to lead 2+. So again, in the sulfate form, it will be able to accept the electrons. Sulfuric acid is the electrolyte medium by which this exchange is occurring. That's where the sulfates are being generated from, is from the acid. So the bottom equation shows the full redox here, and that occurs by combining the half reactions together. So this is an important process. You take the anode and the cathode half reactions, and when you combine them together and cancel out any commonalities on each side, you get the overall net redox reaction. So here's another example dealing with half reactions, and this time with the potential values for each half reaction shown to the right. So you can see the E with the little knot, that's the potential cell, and it's being given some sort of an electrical value in volts there. So this reaction uses a copper anode to plate silver ions onto a silver cathode. And just as the reactions can be summed into a whole, the half potentials can be combined to give the overall cell potential. So most tables that you're going to find are going to provide reduction potential values for half reactions. So be sure to change the sign on the value for the metal that is going to be oxidized. So in this case, copper. If we went into a table and we looked at the reduction potential of copper, it would be about plus 0.337. So we're flipping that to a negative value here because we're looking at the reverse reaction, right? The copper is going to be oxidized when it is at the anode. So anytime you have a reduction potential table, they're giving you the potentials for the reduction reaction. If you want to use one of them as an oxidation or an anode, you have to flip the value there, all right? So if the result is a positive cell potential here, then that means this reaction is going to be spontaneous. So you can see we have the plus 0.518, and that means that the precipitating of silver in this specific setup is going to be a spontaneous chemical reaction. So now we are going to move a bit further into some of the math and equations governing electrochemistry. The first well-known law to be familiar with is Faraday's law of electrochemistry and the Faraday constant that associates with that. So the law states that the amount of any substance to be plated or liberated during electrolysis is proportional to the electric charge that is passed through the reaction. So this charge associates energy per a mole of electrons passed. You're going to find that's common, that we always talk about the mole of electrons that are being passed back and forth in a redox reaction. And so a mole of electrons and the charge associated with that mole of electrons is known as Faraday's constant, which you can see here. And this value is found by multiplying Avogadro's number, because of a mole, with the charge of the electron, the coulomb. And then you're going to obtain this value down here, which is 96,485 coulombs per mole for electrons. And we are going to use this value in multiple equations that are coming up, the first one being Faraday's law. So mathematically, Faraday's law is displayed here, where N is the moles of material, Q is the electric charge, which is sometimes shown as IT, where it represents the current multiplied by the time, if you're using I and T. And then Z represents the number of electrons. And F is, of course, Faraday's constant, if we were to use that. So when discussing further mathematics behind electrolysis, it's also important to consider cell potential, free energy, and equilibrium, which we were kind of talking about earlier. The free energy of the redox reaction can be directly related to the negative product of the standard cell potential. Faraday's constant and the moles of electrons transferred in the reaction. So you can see that in the setup here at the top, okay? This is shown by the top equation, where we have delta G equals negative N, which is the electrons, Faraday's constant, and the cell potential. And there's something important here. What's important is to remember a large negative free energy is correlated with a spontaneous redox. So a larger positive cell potential will also mean spontaneity. So we're looking for positive cell potentials like we saw in that previous example with the silver precipitating. All right, the bottom equation here is known as the Nernst equation, probably one of the best known equations for electrochemistry when students are going through a general chemistry course. And this correlates the cell potential to several factors, but most notably the reaction quotient, which is associated with the redox equilibrium ratio. So we're starting to bring the equilibrium state of the redox in here. So let's look at that in a little bit more detail. So here's the Nernst equation broken down. So we have a cell potential equals, and then there's another cell potential there. So the E naught cell is the cell potential at the standard state. So that means what would it be at 298.15 Kelvin, which is our standard temperature, okay? R is the universal gas constant, 8.314, and that's in the joule format because we're dealing with energy. T is the temperature, so the current temperature that you're looking at, and we'll talk about what happens if you're at 298. That's right below here. N is the moles of electrons. The F is Faraday's constant, and then the Q is, of course, the reaction quotient, which we also associate with K when we're at equilibrium. So, if you take a look at this set down at the bottom, what you have is the 0.0592. Where does that come from? It comes from a simplification of combining Faraday's constant and the R and T constants when you are at 298.15. So this is just a shortcut to memorize this value if you are running your cell potentials at standard temperature, which most of the time, most experiments are going to be run under standard conditions. So you'll see this equation thrown around a lot. Now, one of the things that's important when we're doing this transformation is that the ln of Q becomes the log of Q when we're working with this. So you want to make sure that you change that ln to log, because natural logarithm is using e, whereas log is using base 10. That's a difference that you need to keep in mind when you are switching over between these. All right, so to wrap up the lecture portion here, we're going to look at several different types of batteries and just discuss them for a moment. So first, we have the lead acid battery. That was discussed in prior material, but you're using lead as the primary electrode source, and then you are using sulfuric acid as the electrolyte to help with some of that transfer. So one of the other very common types of batteries is a nickel-cadmium battery. Nickel-cadmium batteries are rechargeable, which is what makes this interesting. So let's talk about that for a second. These batteries use cadmium metal as the anode, and they use nickel hydroxide at the cathode in order to generate a current. Now, how do you get rechargeability? The rechargeability comes into play when these battery cells are going to be supplied with an external current to drive the backwards redox reaction. And this will refresh the chemical state that the original battery was in and the electrodes that were involved. So think about that for a second. Every time you have a rechargeable battery, what do you have to do when the battery starts getting low or run out? You have to plug it into your charger, and you have to allow an electric current to be supplied to reverse the chemical redox that's going on there. Now, if it's spontaneous, which it would be if it's a battery, right, because the battery needs to supply electrical current for whatever device you're using, that means it would be spontaneous. So when you supply the electricity or you supply your charger, you are performing the reverse reaction of what's in there to refresh the state of the battery. So that means that it's a non-spontaneous reaction to reverse it. So you have to supply that current from an electrical outlet in order to drive the battery back to its original state, because that would not be favorable in terms of cell potential or free energy. So then one of the other common ones that we obviously know of is the lithium-ion battery. Lithium ions are probably more common nowadays than the nickel-cadmium. They're just very prevalent in a lot of electronic devices. So they recharge under the same premise, but these batteries can vary a bit more in their composition. The most common is that they utilize a carbon graphite anode and then a lithium cobalt dioxide mixture for the cathode in order to drive the current. So with that, we will go ahead and move over to the practice questions to take a look at some of the math that goes on behind the electrochemistry. So let's get ready to take a look at that. All right, so here we are with the problem solving session. So let's go ahead and take a look at our first sample question, and then we will start working through this here. Now, as usual, I encourage you guys to pause the video, attempt to solve this, and then unpause it when you're ready for the walkthrough. So let's go through this for a second and talk about it. So here's the sample question. Given the following standard reduction potentials at 25 degrees Celsius, and they list them there, you have it for silver, copper, zinc, and iron, which of the following correctly illustrates the use of one metal to displace another from solution? Now note that your choices have two different reaction setups here. So you have iron will precipitate from a mixture of zinc and ferrous ions. Now, stop at that point. That is one claim. Okay, and then you move to the next one. Copper will precipitate from a mixture of silver and cupric ion. So when you are looking at this, you need to consider both of them, and if they are both able to be a correct spontaneous reaction that would flow forward and displace in solution, then that is the correct answer. So another way of stating this is you're looking to find the cell potential for each of the proposed reactions. So the answer that has two positive cell potentials is the one you're going to want to go for. All right, so here's the question. I will let you guys pause it and work on it, and then we will work on this together in just a second. All right, so hopefully everybody had a chance to work through this. Let's go ahead and take a look at this. So what I'm going to do is I'm going to outline the way that you would go about solving this. So let's take example A, where it says iron will precipitate from a mixture of zinc and ferrous ions, and then the copper and silver example as well. So to get started, let's look at the zinc and the iron. So the half potentials that are given to you, we're going to be utilizing this material up here. All right. Now you have to pay attention to the value that you're going to use, because remember, if something's going to be an anode, these are reduction potentials. So whichever one is going to be oxidized, you need to be paying attention to the sign, the value, whether it's positive or negative, right? We have to flip what's given to us in the reduction potentials. So the way that you would start this is you would say, all right, I've got zinc that's solid, and then that's going to go to the aqueous zinc 2+, plus I get 2 electrons out of that transfer. And the value up from that table, okay, that I need to place here is going to be plus 0.763 volts. Now, why is it plus? Up here it's negative. It's plus because I used the reverse reaction, right? I'm not going from zinc 2+ to zinc solid. I'm going from zinc solid to zinc 2+. And so that is going to be an oxidation, not a reduction. So I need to flip the value that was given to me. Now with the iron is going to be reduced, so I can keep the reduction potential value up from that table. So I have iron 2+, aqueous, plus 2 electrons that it's receiving from the redox reaction. And then I have iron solid. Now this reaction is going to have the E cell of negative 0.44 volts. Now all we're really concerned with here is the cell potential. So you could also write out the full redox reaction by summing all of this up, but we're just interested in seeing this value here. So this value comes out to plus 0.32, okay, and that's volts. And if I take a look at this, this is positive. So that means this would be a spontaneous reaction. So the first of the two selections that we're making here are legitimate, all right? So we can go up and make a mark for ourselves and say the iron. Yes, this one is good. So now the question is, will the copper and the silver work out the same way, right? So let's go down and look. So now I'm going to do the silver. So I have 2 silver solid, and that's going to go to 2 silver ions plus the 2 electrons. Okay. Now, if you look at the equation that they have up there, it's a single silver going to silver plus 1 electron, because it is silver plus. So I have to do that 2 times over because the copper is copper 2+. So I need 2 electrons in order to work with this. Right? So then I have copper 2+, aqueous, plus the 2 electrons is going to go to copper solid. All right, now the potentials that you would grab from the table here are going to be negative 0.855, and then plus 0.337 for the copper. So I bring those together, and I get negative 0.518. And that means no. Negative cell potential is going to lead to a positive free energy. This is not spontaneous, and the reaction is asking us which one of them will proceed forward to deposit the metal. This one would require a current. It's not going to be able to go forward at the current setup that we have here. All right, so that would eliminate choice A. Now what you would want to do is you would want to go through and work on this for all of the potential reactions. Now what you can also notice here is that if we have copper and silver, and we know that copper and silver will not work, copper and silver, we can see down here it says copper and silver, right? So let's be smart. If you were going through this, we can already say D is out because we know that one doesn't work. And we also know that the iron and the zinc will work. So if we know that the iron and the zinc will work, we have another one down here with iron and zinc. We already know that that would work. Okay? So this is the most likely answer. You would want to go through and check the silver and the copper. So notice that this is the reverse of this reaction up here. We have copper will precipitate from a silver and copper ion mixture. And here we're saying that silver will precipitate from a mixture of copper and silver ion. Well, let's think for 1 second. If this was non-spontaneous, the reverse reaction must be spontaneous. That must work. So without even having to do more math, we're done. We know that C is the correct answer here. And C would be the correct answer in this sample question. So keep in mind, when you're working through this, okay, you always want to look for shortcuts like that where you can harness your knowledge to say, well, if I just did this work and I already proved it to myself, it eliminates this choice, and I know the reverse of it must be true, so then C is true, right? We only had to do the math once. It would be very foolish to continuously work this out and not take advantage of that, especially when you're against timetables. So that is the first question. Let's take a look at one more here. So question 2. A voltaic cell, remember that's galvanic is the type of term that we're talking about, is constructed by placing nickel metal and nickel chloride in 2 beakers, A and B, maintained at 25 degrees Celsius. So that's an important note. We're going to be at standard temperature here. Beaker A contains 1 molarity nickel chloride, whereas beaker B contains 0.1 molarity nickel chloride. The 2 beakers are connected by a salt bridge. So if you look at this here, okay, and this double line right here, that represents the separation of the cell. So we've got like, you know, we've got the one cell over here, and then we have the other cell over here. So when we had that example with the 2 beakers, right, we've got the 2 cells here. So you might even want to draw this out while you're working with it and draw the cell out so that you can represent it to yourself. But that's what we're working with. Now note, the electrodes are both nickel. So if we have 2 nickel electrodes, this is actually a special type of voltaic cell. This is going to be a concentration cell because we have the same 2 electrodes and we have different concentrations of the electrolyte solutions that they are found with. So given the R, universal gas constant, joules per mole inverse Kelvin, and Faraday's constant, it is asking what is the direction of the spontaneous electron flow in this cell? That's number 1. And number 2, what is the value of E cell for the voltaic cell indicated above? So if you take a look here, okay, A, B, C, and D. So the first thing you're determining is from beaker A to B or from beaker B to A. You're determining the flow of the electrons. That's part 1. And then for part 2, you are determining the actual voltage here for the E cell. Now keep in mind that these are both the same electrodes. So the flow forwards and backwards, right, in terms of the E cell, you're going to generate a current, but the half reactions are really the same here. They're just the inverse of one another, whether you're doing oxidation or reduction. We don't have 2 different metals, okay? So that's important. All right, so go ahead and make an attempt at this problem, and then when you're ready, unpause the video and we'll work through it. Okay, so hopefully everybody had a chance to work through that. What I'm going to do is solve question 1, and then we'll solve part 2 here. So question 1 is probably going to be the easier part. You really don't need a whole lot of math for this. You're going to set up your cell. I'm going to do it visually here. Okay, so I've got my 2 cells. They need a salt bridge connecting them. I should say my 2 half cells. Right, so there's my salt bridge. And then I've got nickel and nickel. They're both going to be nickel. And then I'm going to have nickel 2 plus, right, and nickel 2 plus in my electrolyte solution. So this is from the nickel chloride. Now it says that here's A and here's B. The question says that A is going to be at 1 molarity and B is going to be at 0.1 molarity. So the question is, how is the flow of electrons going to occur in this connection here, or this cell setup? So you're going to look to generate electrons until the equilibrium is established in a concentration cell. So if we think about this, we've got B as the weaker of the two, and when I say weaker, I'm referring to the concentration. Okay, so if this is weaker, it needs more of the nickel 2 plus in order to become stronger in concentration. So how are we going to generate nickel 2 plus? We need to take solid nickel and we need to turn it into nickel 2 plus. Well, that's a process of oxidation. So I'm going to label this as the anode, and that means by default this has to be the cathode. Right? And it makes sense that this is the cathode, because if we're trying to increase the weaker concentration, we're going to try to decrease the molarity over here. How do I decrease it? I take nickel 2 plus and I make sure that it goes to nickel solid. It needs to get plated onto the electrode. So it's going to be going this way and plating onto the electrode. And so where do the electrons go? They're removed from the nickel in the anode in order to make nickel 2 plus, and then 2 electrons are sent over in order to remove nickel 2 plus, right? So the 2 electrons are donated here in order to plate to solid nickel. So that is going to mean that when we look at this, B is where the electrons are generated and they will flow to A. So what examples do we have here? We have from A to B, no. We have from B to A, possibly. We have from A to B, no. And we have from B to A, possibly. So now the question is it going to be 0.03 volts or 0.06 volts when we get ready to look at the Nernst equation? So that's what we need to find. We need to find that cell potential associated with it here. All right, so we're down to a 50-50 shot already, just from that general analysis. So then we move forward, and what we're going to do is we're going to set up a situation where we say E cell is going to be equal to E cell standard. Okay. And remember, we're at standard state, we're at standard temperature. I pointed that out earlier. So that's going to be minus 0.0592 over N. And then you're going to have log, not ln, of Q. All right? And what's really important here, because the potential at standard is going to be both the reactions, right, are going to be the opposite of one another. They're going to cancel one another out there. So what we're really looking at is this. All right? That's what's of interest here. So all you have to do is work your math out here, and you're going to get negative 0.0592. How many electrons are transferred? How many moles of electrons? Well, we just said from our example up here, nickel 2 plus, it's 2 electrons. So we just need to plug in 2 down here. We're talking about stoichiometric electron ratios. And then the logarithm, right? And now we need to look at the redox. And the redox says that it is going to be 1 molarity, right, over 0.1 molarity. And so if we look at that, and we solve for that, that's going to be the log of 10, all right, and that is going to, when you plug it all in, equal negative 0.03 volts. And so that means that B is the correct answer that we would want to select here. All right, so that is an overview of some of the types of questions you might come across regarding electrochemistry on the MCAT. And that's going to conclude our presentation on electrochemistry. So we hope you found it informative, and we will see everybody for future lectures on other material.